We also need our motor that we built together last time. And our Velcro dots that we've been using. We also need our worksheet that says lesson 3 on it. This is where we're going to record our observations for today. We also need some tape, some pennies or washers from your house, something to write with, so a pencil, a marker, a pen, and some scissors. If you have a ruler, that'd be really nice to have. We're going to give our other science friends just about 1 more minute, just in case someone's running late. I see Ethan has a worksheet. Thank you for showing me that. Who here is back in school in person? I see 2 of us go to school in person. Does anyone here go to school online? Yeah, I do too. Do we like school so far? Yay. Okay. So we're going to play Science Says again. This is to make sure we have all of our supplies. So Science says, show me some tape. Can we balance the roll of tape on our head? Great job. Thank you. Science says, show me some pennies or washers. I've got pennies in here. I've got some washers. As long as we have some coins, it'll work. I see Marlo has some. Yes, I see we have a hand raised. Do you want to unmute yourself?
My mom is getting some pennies.
Excellent. Thank you. Yeah, don't worry. We're going to play Science Says for a little bit longer. That way we all make sure we have our supplies before we start. Show me some scissors. I didn't say Science Says. What about if I said Science Says, show me scissors? Excellent. I see a bunch of scissors. These will help us. Thank you, guys. Science says, show me your motor unit that we already built. Excellent. Thank you. I also want to remind everybody that I'm using your camera right now. This helps me so I can see what step you're on in the project, and so I know that nobody's confused. It really helps me if everybody can keep their camera on for the entire class. Thank you. Just wanted to make sure that everybody knew that that would really help me. One last one. Science says, show me your Velcro dots. Excellent. Thank you all. I'm going to paste again all of our materials into the chat just in case someone's lost on materials. We know what they are. Okay, to start today, what we're going to do is we're going to be thinking about momentum. I'm going to share a screen here with you all. Can everybody see these balls on the screen? Give me a thumbs up or thumbs down. No? Oh, Ercy sees balls. Does anyone else see them? Ethan does not. Okay, I'm gonna try again. Because it looks like about half of us can see them. Maybe if I also highlight my video, that might help you guys, huh? Spotlight video. There we go. That should be bigger now. Yay! Okay, so we're going to think about these two balls and try to compare and contrast them. It means we want to think about the things that are alike between them, how they're similar, and then we're going to think about which ways they're different. Who wants to raise their hand and share one thing? Yes, Marlo.
They're both round.
Yes, they're both round. So we're looking at physical characteristics. Who else has something they want to share? Cooper?
One of the balls has holes and one of them doesn't.
Ooh, that's another great observation. So we are noticing that the surface is different, that there's holes. And our baseball does not have holes. Ethan?
The baseball has red stripes and the bowling ball does not.
Ooh, so this is color that we're noticing, the pigment. Marlo, you want to share again? Can you unmute yourself?
One's heavier than the other.
One's heavier than the other. Let's all imagine picking up our baseball. We can pick that up pretty easily with one hand, right? What about our bowling ball? It's pretty heavy, right? If we have a really heavy one, we might want to carry it with both hands. Maybe we're carrying it and we're like, oh, this is really heavy. We're picking it up with just 3 fingers. This is because it has more mass. There's more stuff shoved into there. It's really dense. It's also larger. So a bowling ball is really big. Baseball can fit in my hand. We're going to keep the idea of weight in our head. We're going to imagine putting them on a big hill. Who wants to share what they think would happen if we put these on a big hill? Yes, Marlo.
The bowling ball would go faster.
Ooh, so you're saying that mass affects the gravitational pull and the speed that our objects would move at. Excellent. So our big, heavy bowling ball would roll down the hill faster. Yes, Ethan.
The um the baseball would bounce higher.
Ooh, so if we were to try bouncing them instead of rolling them down the hill, it might. What about if we were to stand at the bottom of the hill while we roll these down and they were to hit us? That'd probably hurt, right? Which one would hurt more, do you think? The baseball or the bowling ball? Yes, Marlo, what do you think?
The bowling ball.
Ooh, yeah, it would go faster and there's more weight. This is because of momentum. Our bowling ball really wants to keep moving. It'll keep moving even if we're in the way. It will hit us. The baseball that's rolling at a slower speed with less weight will come to a stop faster. It won't put as much pressure on us. Won't hit us as hard. Has less momentum than our giant, heavy bowling ball would. We're going to do an activity together to talk about momentum. We're going to need our styrofoam plate. We are going to also need our tape and our pennies or washers. Our goal of this activity is to make our plate move really far and fast. Who has an idea how we can move our plate? Yes, Ethan.
We could throw it.
We could throw it. That would work. Are we going to throw it in the air? Or are we going to throw
Yes.
it on the floor?
Throw it in the air.
So that's one way we can move it. Marlo, what's another idea of how we can move our plate?
If we roll it.
We could roll it like a giant wheel across our floor or our table. Who else has an idea of how we can move our plate? Can we pull our plate? Drag it along the table? Ethan, do you want to unmute yourself?
We could blow on it.
We could blow on it to apply pressure. We could also push it across the table. We are going to try a couple of these ideas. We're going to try to roll it, and we're going to try to push it across our table. And we're going to come back and share what we discovered. You can also use the ground if you don't have very much room on your table. So we're rolling our plate or pushing our plate. Okay, who wants to share which method of moving their plate allowed their plate to move farthest? Yes, Ethan.
So when I rolled the plate, it didn't really go as far because it kept tipping over. But when I pushed it, it went farther.
Did we use the same amount of force on both? That means
Yeah.
Excellent observation. Thank you, Ethan. Did everybody agree with what Ethan said? Did your plate move farthest when you pushed it instead of rolled it? Cooper says no. Do you want to explain what you observed?
So I tried to throw it like a disc. It didn't work, or just throw it like that. Didn't work.
Ooh.
Kept tipping.
Yeah, so we're seeing we have a bunch of balance issues. Our plate doesn't want to stay on the small surface, this little rim. It wants to fall over. We can try to balance it on our table and see the same issue. It wants to fall over to one side, doesn't it? We are going to try to be inventors. We're going to try to make a way that our plate will still be able to move, but on its surface like this. We have pennies and tape. We are going to try to make it so we can roll it really far and fast. What we're going to do is we're going to record on one side of our worksheet how it moved when we rolled it without adding anything to our plate. Then we're going to spend 5 minutes and we're going to modify our plate. That means we can add our pennies or washers to it. And you can also cut it if you want. And then we're going to record our new observations of our modified plate. So we should write our observations about what we've already seen. We can write and we can draw to record our observations. When you have put your observations on your sheet, you can start your modifications of your plate. It means you can start changing your plate. I will tell you when you have 1 minute left. That way you can make sure you test your new plate. We have about 3 minutes left to modify and test our plate. if you have not tested your plate yet, you should do so soon. We have about 1 minute left. Okay, we're going to come back together and share our observations. Ethan wants to start with telling us what he observed.
First, when I rolled the plate, it kept tipping over. But when I added the weight, it then bounced a little and then fell. So it went better with the weights.
Ooh, so we notice that our object, our plate, wants to move more when it has more weight, it has more mass. Who thought that their plate moved faster when they added extra weights? Marlo did, RC did, Cooper, you also thought it moved faster. We just saw that momentum, how an object wants to keep moving, is due to its weight and its speed. Great job. You guys just learned one of our things that they learn in physics about momentum. Who else?
There's my plate rolling and jumping.
Ooh,
There's my plate rolling and jumping.
Ethan tells us that it bounces and it rolls. Thank you, Ethan, for your observation. Ertzi has an observation she wants to share.
So I drew this. So here's how it went. So
Ooh, yes.
this one is how it went with the added weights. And this one is how it went without the weights. Without the weights, it just went straight up and straight down. And with the weights, it went in a loop-de-loop before going down.
Ooh, you learned about angular momentum, how it wants to spin. Excellent job. Thank you. Who else wants to share an observation that they just made? Oh, it looks like Lily made something with her plate. Do you want to share?
So I just I cut the middle out and then put washers on this side, and when I rolled it, it went faster and flew a little.
Ooh. So you have less surface area, but you have more weight. That's a neat observation. Thank you for showing that to us, Lily. We're going to have one more observation shared before we move on. Does anyone want to share our last observation? No? Okay, we'll do it together then. Who thought their plate will continue to roll for a longer amount of time now? Did anyone notice that it rolls for a longer amount of time? Ooh, yes. So when we add more weight, our object wants to stay in motion for longer. till it falls over or it runs into something, right? Excellent job, everybody. Thank you for being inventors with me. So I gave you a question or a problem to solve, which was that we wanted our plate to roll. And you used the tools around you, your materials, to come up with something new all by yourself. You were an inventor. Thank you. Who is ready to start making their robot for today? Excellent. So what we're going to need is our pie tin, our motor unit, our tape, our Velcro.
No, mine didn't work because it had too much weight.
Ooh. So I think that was Marlo who just shared, right? So someone said that when we add a lot of weight that their paper plate didn't roll. Thank you for the observation. We're gonna move on to our robot now. Does everybody have all those supplies I listed? Yeah? Excellent. We are going to test our motor first. Where we know that we have a way to move our robot. Who remembers how our motor works? Oh, I see Ethan understands how his motor works. I saw his moving. We have to make our circuit complete. It has to be a big circle, big loop. Our electricity has to flow from our battery into our motor, back through our battery. So we're going to connect our paper clips to our loops on our motor. It should spin. Does everybody's motor spin? Excellent. So our batteries only have a certain amount of energy stored in them. So we're going to make sure that we take one of our paper clips off of our motor now. We just want to make sure it worked before we start making our robot. This is going to be the body of our robot for today. Who has an idea of what we can do to change this body so it's a robot and it will move around? Yes, I see Ethan's brother has an idea. You are raising your hand. Does Ethan want to help with unmuting? Yeah, what's your idea?
With our hands.
Ooh, our hands. So we can apply force with our hands to move our pie tin robot. How else could we move it? Ertzi, do you want to unmute yourself? Tell us your idea.
Add legs.
We could add legs. But would legs by themselves move our robot? No. What would we have to do to make our robot so it can move on its own?
Do it as a propeller.
A propeller. That's a neat idea. So propellers help helicopters move. But what powers the propeller? Who thinks we could add a motor or an engine? Yeah, we have a motor already built. So we can add our motor to our robot. Let's look at the back of what we already built for our motor. Does everybody have 2 pieces of Velcro on the back of their motor? If you do not have 2 pieces of Velcro, I need you to add a second. Excellent. I see that none of our Velcro has fallen off. We're going to rub our Velcro. Does our Velcro feel really hard and made out of plastic loops? Does it feel soft? Who says it feels hard? It's our loop side of our Velcro. Yeah. So what side of our Velcro should we be placing on our robot body if we want it to stick? All right, see, you're raising your hand. Can you unmute yourself?
These soft Velcro dots.
Yes, our soft bunny side of our Velcro. Our hook side of our Velcro. So what we're going to do is we're going to pick up our hook side of our Velcro, the soft bunny side. We're going to stick them to our Velcro dots we have on our motor. We want to make sure we have 2 on there, 1 for each of our Velcro dots. Okay, it looks like Lily has gotten back into our group. Excellent. We are now going to put our motor onto our pie tin. We want to make sure that our wheel is over the edge of our pie tin. We don't want our wheel up against the edge, otherwise it can't turn by itself. We're going to stick our hand inside of our pie tin. We're going to push down with our other hand where our Velcro dots are. It's attached really securely. Yes, Ethan's brother. Do you want to unmute? That way you can ask your question or make a comment. No? Okay. So we now have our body of our robot. We can test it out on our desk. We can attach our paper clip to our other side of our engine and set our robot down and watch it move. I'm going to give you guys about 1 minute to test out your new robot. Remember, you can hook your paper clip through that loop on your engine, on your motor. Yes, you're raising your hand, Ethan. Can you unmute yourself?
Is this a fighting robot?
It will fight. Who likes their robot right now?
I do.
Ooh. Who would want to change their robot? Yeah, I see a couple of us want to change their robot.
I could show you how mine moves.
This robot moves around a lot. Who else's robot moves around a lot? That's a great observation. We're noticing that our robots move. That was our goal, was to make a robot that moved by itself, right? Yeah. Okay. So we have a couple ways that we can modify our robot. We can bend our pie tin. We can use our tape and paper or cardstock to add to our robot. So we are going to take about 5 minutes and change our robot in any way that we want. That way, all of our robots work a little bit different from each other's. So we can bend our pie tin. We could also cut it if we want. But remember, if we cut it, it's going to be really hard to put back together. So we want to think really carefully before we cut it. We can also use our paper to attach it to our robot using tape. Ooh, Arlo has something she's going to attach to her robot. So we're going to spend about 5 minutes modifying our robot. If you have any extra pennies or washers left, you can also use those to modify your robot. I see Marlo showing me a modification of a robot. We're going to spend about 3 more minutes before we come back together and share what our robots now look like. Oh, I see Lily's modifications to our robot. Excellent. We're going to spend about 1 more minute on our robots, and we're going to finish up. So we should be making our last changes to our robots right now before we share what they look like with everybody else. Yes, Ethan, do you want to unmute yourself?
I put a taped bottom on my robot.
Ooh, you gave it a surface on the bottom to move on. cool modification. Yes, Ertzi.
You see if it still moves though.
So I stuck pieces of paper with things onto my robot. This one says Red Bolt and has a red lightning bolt on it. And on the front, I gave it a gangster face.
Oh, wow. You decorated your robot? Excellent. By decorating it, you also added some extra weight. We're going to see how that works. We just learned about how weight helps objects for momentum. Maybe we'll help your robot even more. We're going to find out, aren't we? Okay, everybody who's still working on your robot, we're going to finish up because now we're going to test them. So we need to remember back to how our robot moved before we modified it. Think really hard. How did it move? Yeah. Now we're going to connect our wires to complete the circuit again. We're going to stick our paper clip through our little loop on our motor. We're going to watch how our robot moves now. Does your robot move better now? Do you like how it moves? Do we think it needs to be modified further? We're going to have our last round of modifications to our robot before we battle them. So we can continue to test our robot, or we can modify it for the next 2 minutes. Then we're going to begin our battles. We have about 1 more minute for testing our robot or modifying it before we begin our battles of the robots. Okay, it's time to start our battles. What we're going to do is we're going to put our worksheet on our desk. It doesn't matter which side's up. We just want our worksheet on our desk. We are then going to put our robot in the center of our worksheet. Our goal here is to find out which robot moves the fastest and which one moves the slowest. Both of those robots are going to get a shout out, a reward of saying that they are the winner of our first battle. So what we're going to do is we are going to connect our paper clip to our motor. But we're going to use our hand to hold our robot in place. That way I can give us a countdown so they all start at the same time. when your robot moves off of your paper, you're going to raise your hand. Okay? Marlo has a question. Do you want to unmute yourself?
The part of the wire that was connected to the paper clip fell off of like it fell off of my paper clip, and now I can't attach it because there's not enough wire.
Okay. Could you have a parent help you strip your wire again? So you're going to use those wire strippers, and you're going to strip off about 1 inch of the insulating, the plastic part around your wire, so you can connect your paper clip again. When your robot's ready, we'll probably be ready to have our second round of robot battles. It's everybody's robot in the center of their paper. I'm going to give us a countdown. When I say go, we're going to release our hand from our robot and watch as it moves. So we're going to put our paper clip into our motor. 5, 4, 3, 2, 1, go! Raise your hand when yours gets off of its paper. Cooper's was the fastest robot. His moved off of his paper first. We still have to assign who the slowest robot is for a prize as well. I see some of our robots are not afraid of the other battling robots. They're okay staying in the ring. Looks like Ethan's and Ertzi's both are okay staying in the ring and they're not afraid. And Lily, it doesn't look like you have a ring for battling yours. We're gonna give them about 30 more seconds. We're gonna see if we have our winner. Oh, Ethan's robot's left. Means Ertzi. It's our last robot that stayed in the ring. Great job. So we have our 2 winning robots. We have our fastest, that's Cooper's. We have Ertzi's. It was the least afraid. It was okay staying in a ring. Okay. We're going to do another robot battle now. What we're going to do is we are going to put our paper on our desk again. For this robot battle, we're going to see which robot crosses the ring, means steps outside and touches the table the most. So we have to count the amount of times that our robot crosses off of the paper in 2 minutes. So we're going to put our robot back in the center of our paper. And I'm going to give us a countdown. I need all of you to count how many times your robot touches the table. Okay. 5, 4, 3, 2, 1. Let the races begin. So we need to make sure we count how many times our robot crosses our paper and touches our table. Oh, Lily, I think you have something under your paper. So your robot's moving the entire paper. We're gonna give our robots about 1 more minute. We are making sure we're counting how many times it touches the table. Okay, we're going to use our fingers on our hands to tell each other how many times our robot touched the table. Before we do this, we are going to make sure that one of our paper clips is disconnected from our motor. We don't want to waste all the energy inside of our battery. So we're going to turn off our robot by disconnecting one of our paper clips. Then we're going to use our hands to put up the amount of fingers. How many times our robot touched the table? Cooper says his robot touched the table 6 times. Ethan did 4. Ooh, Ertzi's did 12. Lily did 4. Marlo did 0. Okay, so Marlo had the least amount of times that her robot stepped out of the ring. Ertzi did the most times that her robot moved out of the ring. Great job. Thank you for taking down this data about what your robot did. You observed the movement of your robot. You recorded what it did by counting the amount of times that it touched the table. This is what scientists do. They record data. You guys were great scientists today. You made an invention. You learned about momentum. You modified a robot and made it, meaning you were an engineer. And you also took down data. Thank you, guys. We're going to think about momentum one last time before we leave today. Let me spotlight my video so it's nice and big for everybody. So we were saying that our bowling ball would move the fastest if we rolled it down the hill, and it would have the most momentum if we rolled it down the hill. That means it would smash into us really hard if we were underneath it. We have 3 objects here. We have our baseball, we have a really small car, we have a really, really big truck. If all 3 of these were to move at the same speed and we stood in front of them, which one do you think would hurt us the most? Yes, Ethan.
The truck.
Ooh, Ethan thinks it's the truck. Who agrees with Ethan? The truck has the most momentum. Yeah, has the most mass. All 3 of these objects moved at the same speed, the truck would smash into us the hardest, would give us the most momentum that it would transfer into us, so it would hurt us the most. This is why we need to be careful that we don't cross in front of traffic, because they have a lot of momentum. Cars don't stop easily. Yeah, it means all that pressure would be moved into us, be transferred into us. That causes injuries. Thank you, guys. We're going to use our hands to talk about what our favorite part of today was. Whose favorite part of today was doing inventions? Whose favorite part of today was modifying their robot, being an engineer? Whose favorite part of today was watching their robot move, being a data collector? Excellent. So I see that across our class, we have different favorite parts of science. It's really cool that science has all these different things that you can do. There's a whole bunch of jobs in science. So there can be something of a job, anything you like. Yeah, it's important that you stay doing things that you enjoy. Oh, you have a cool job that you also enjoy. Thank you guys for doing science with me today. We're going to make another robot next week. We need to make sure that our motor unit comes back to class with us next week. If you're noticing that your motor unit needs to be fixed at all, let's try to do that before we come to class again. That means we might need to strip our wires if we broke them. Or if our paper clip fell off, we can put it back on. Or if your battery's dead, we want to make sure we replace it, okay? Thank you guys, and I'll see you all next week. Bye-bye.